our next speaker is Bob Zubrin. Everybody knows. How many of you know Bob Zubrin? There's no bio for Bob. There we go.
I can. All right. Thank you very much. So, and I want to thank the conference, John Mankins, Madhu, for providing me with this special double slot to show you a presentation that I think is of some importance. Okay, I'm going to lay out what I believe is a truly cost-effective architecture for enabling human exploration of the moon. Okay, now, in any engineering process, the first thing you need to do is define the requirements. Okay, while it is, of course, important in engineering to design things right, it is impossible to do that unless you are designing the right thing. Okay, right. So that's the key thing here. Okay, now, in my view, the requirements for a highly effective lunar exploration program includes and I'm talking about the transportation system part of it, because that's what I'm presenting, is maximum access to the lunar surface, minimum development and recurring cost, minimum schedule, and minimum risk. Okay, now, this is exactly the opposite of what we're seeing in the program of record right now with the Lunar Orbit Gateway, in which you have minimum access to the lunar surface, maximum development and recurring cost, maximum schedule, and maximum risk. Okay, so look, let's with that program, there is no why, there is only do. Okay, so what is it if we go to this from a requirements-driven perspective? The number one requirement for exploration is mobility. Now, the moon is not a small place. The moon, as Kraft Erica used to say, is a continent the size of Africa. Okay, to say you would explore Africa by going to one location on the coast, okay, or would be absurd. Now, the moon, of course, it's big, the terrain is rough, there's no roads, there's no railroads, there's no rivers, okay. If you're going to travel any distance on the moon, you're going to have to fly. That's the only way to do it. Okay, so we're talking about long-distance flight on the moon. This can obviously not be done with wings, but it can be done with rocket-propelled vehicles. Now, if we look at the first chart here on the left, what I'm showing you is with a rocket-propelled vehicle, okay, the range of the vehicle as a function of its delta V capability. Okay, the range is in blue, and the fraction of the lunar surface that becomes available to that is in orange. And what you can see is that at 6,000 meters a second, 6 kilometers a second, the range of the vehicle is several thousand kilometers, and the fraction of the moon that is available to the vehicle is about 40%. And you can see it's really rather steep. If your delta V capability is 4 kilometers a second, you only got 3% of the moon within range. Okay, so 6 kilometers a second is the magic number to get some really substantial part of the moon available to you. Now, more is better, but 6 gives you something really to deal with here. Now, 6 is also a very interesting number for another reasons, because 6 kilometers a second is the delta V required to take off from the surface of the moon, go into trans-Earth injection, and do a propulsive capture in low Earth orbit. Okay, so 6 kilometers a second takes you all the way from the lunar surface to the ISS, or to a rendezvous with a Dragon or an Orion or a Sierra Nevada or whatever is there. Okay, so that's a really interesting number. Can we do it? Well, the chart on the right shows you, let's say you had a 2-ton dry mass vehicle. Now, there's a very famous vehicle that was a 2-ton dry mass lunar vehicle. It was called the LEM. The manned vehicle that we used in Apollo to descend to the surface and return to orbit was 2 tons. And that was done with 1960s materials. Okay. They didn't have Kevlar, they didn't have graphite overwrapped, they didn't have anything like that. They had aluminum. Okay. All right. And what you see, if we're doing hydrogen-oxygen propulsion, that the total of the 2-ton dry mass at 6 kilometers a second We still have 1.5 tons available as the payload. Only half a ton is needed for tanks, engines, and so on. And the total mass of the vehicle is 8 tons. So there's 6 tons of propellant, 2 tons dry. That's what it is. So for this thing to do its 6 kilometers a second delta V, it needs 6 tons of propellant. Okay. Now, given that that is what we actually need to be effective on the moon, and there's no point going to the moon unless you can be effective when you get there, how do we organize a transportation system given the availability of that? And this is where I come up with the Moon Direct plan. Now, there are 3 phases to the plan. The first phase is we're going to pre-place some cargo, some habitation modules, a power system, things like that, on the moon. These are unmanned missions. They go one way from the surface of the Earth to the surface of the moon. Okay. The second phase are initial piloted missions, okay, to the moon. They go to this base. And they are distinguished from what follows because in these initial missions, it is assumed that in situ propellant is not yet available. So these missions are being flown without that ability. Then in phase 3, once they make ISRU available, or ISPP, in situ propellant production, we can do recurring piloted missions with the assistance of in situ propellant. So schematically, here it is. Phase 1 on the left are base emplacement. We land some habitation modules on the moon and a power system, whatever. So these are one-way cargo missions. Okay. Phase 2, initial crewed landing, and I'll explain how this works. And phase 3, recurring crew missions, which take advantage of in situ propellant that has been made available by the apparatus established in phase 2. All right, now if we want to deliver cargo one way to the moon, we have a number of option vehicles available. Of course, there's the Falcon Heavy. It can do 62 tons to low Earth orbit, or 26 tons to geosynchronous transfer orbit. Geosynchronous transfer orbit is a highly elliptical orbit, and it gets you actually most of the way to translunar injection. And this vehicle is actually designed for that purpose because that's the standard commercial mission. Okay, and we could stage off of it at that point. And then I've looked at 2 different kinds of landers, either methane oxygen or hydrogen oxygen. Then there's the New Glenn. Now, by the way, in these figures for the New Glenn here, I was using 45 tons to Leo, which is the published figure, but I think they maybe do better than that. They've just upgraded the New Glenn. They replaced the capacity of the BE4 engine. They moved it up from 400,000 pounds to 550,000 pounds. That's a 33% increase in capacity. That should be reflected in the payload, and they may be able to get 60 tons, in which case their capacities will be similar to the Falcon Heavy and not substantially less. And it does have the advantage of a bigger fairing, a 7-meter fairing instead of a 5-meter fairing. So these New Glenn figures are based on the earlier data, and they may need to be revised upward towards about what the Falcon Heavy can do. Then there's the Vulcan. It's only 30 tons to Leo. It's actually significantly less than the Falcon Heavy. SLS, if you had it, it would be more, and BFR, much more. Now, what you see here over on the far right column is the payload delivered to the surface. And we see the Falcon Heavy can deliver payloads on the order of 8 to 10 tons to the surface. The New Glenn, it's more like 6 or 7 unless we assume this upgrade gets it to Falcon Heavy, in which case they're the same. Vulcan substantially less, SLS and BFR are more. But 8 tons, think about this for a minute. Our lunar excursion vehicle has a wet mass of 8 tons. So, with the Falcon Heavy and possibly the New Glenn, you could deliver that wet to the lunar surface so that in phase 2, you can send missions there before you have lunar propellant available for you. All right? So we can send HAB modules weighing 8 tons, boom, land them on the surface, have substantial houses on the moon. We can deliver a power system. All that's there before the astronauts show up. Then, okay, so that's phase 1, which we could do then. I figure land a HAB module as one important cargo, and then another cargo module containing all sorts of gear, solar panels, and also a microwave system, as I'll show, that will be what the astronauts need to get things going. Okay, so this brings us now to phase 2. Okay, so now we have a house on the moon, we've got another payload module, so this takes 2 Falcon Heavies to do. 2 Falcon Heavy launches to do phase 1. Okay, if you want more stuff, then 3 Falcon Heavies. Okay, but now we do phase 2. Now this is how we do it. Okay, the Falcon Heavy is not man-rated, and Musk does not intend to make it so. New Glenn presumably will be man-rated, so you could alter this. But I'm assuming Falcon Heavy because we've seen that fly, and haven't seen the other one yet. All right. It delivers a cargo lander to low Earth orbit, and its cargo is a wet lunar excursion vehicle. I call it the LEV, Lunar Excursion Vehicle. Lightweight vehicle comparable to the Apollo 11, except it is a single-stage vehicle that runs on hydrogen oxygen with a delta V capability of 6 kilometers a second. A Falcon 9 launches the crew to orbit in a Dragon. They rendezvous. The crew transfers from the Dragon to the LEV. The LEV then flies, is flown by the cargo module, because this is a wet LEV being flown with the crew in it, and lands at the lunar base. The Dragon stays behind in low Earth orbit. This is different from Apollo, where they sent the capsule all the way to low lunar orbit. Okay, here I'm leaving it behind in low Earth orbit. Okay, the crew flies to the surface in the LEV. They then can enter the hab, live there. They take the gear out of the cargo module. They set up the solar panels and the other gear. They get everything going. Okay, and then they set about the task of making propellant on the moon. Now, the place where we would want to put this base is probably near the south pole of the moon, possibly north pole, but there's been the most discussion of the south pole as a place where there is a crater in which is permanently shadowed, in which is almost certainly large amounts of frozen water, either as ice or permafrost or other forms. Okay, relatively near highlands that are nearly almost always illuminated. We've landed the HABs, obviously, in the illuminated place, and we set up a microwave transmitter on the rim of the crater so it can beam power into the crater. All right, now people in the NSS have heard about power beaming. It was O'Neill's idea, 22,000 miles beaming power down from GEO to Earth and all that. That's hard to do. But it's much easier to beam power a kilometer, 5 kilometers, 10 kilometers. This has been done. Okay, this has been done. And we would do it. Now, there's a number of ways to do it. For short range, that is, ranges on the order of a kilometer, you have the simplest possible system. You could broadcast microwaves on the same sort of frequencies as your kitchen microwave of a 12 centimeter wavelength. And just have a transparent dome with a reflective back, and it would be reflected right down into the surface and into the ground. It would heat the subsurface. Vapor would come up, and then you have a vent into a refrigerated tank. Well, you don't even have to refrigerate it. You're sitting in 40 Kelvin. And you got the best refrigerator in the inner solar system working for it. Okay, and it condenses there, and after that thing is filled up with ice, you close off the valve, and that thing is then driven out of the crater to the base, where the water is melted and electrolyzed and turned into hydrogen oxygen propellant. If this was further away, you would have to do something like beaming the power with a higher frequency. You can go to millimeter wave, you get a factor of 100 increase in range. Now you can go 100 kilometers. But then you would only be heating the surface, and that may or may not be adequate. If it's truly ice, that is adequate. If it's not, if it's underground stuff, you might have to convert the beam power to electricity and then into microwaves at a lower frequency, longer wavelengths to go deeper. But this is the general idea. So a key technology for an effective lunar base is short distance power beaming. Okay. We don't need long distance, we don't need thousands of kilometers, but we need 10 kilometer kind of power beaming, and this we can do. And now we get to phase 3. Now this is the real fun part. Because now we have propellant on the moon. So we don't need to fly to the moon in a wet LEV. We can fly to the moon in a lunar excursion vehicle that is fueled in LEO itself and flies one way to the moon, 6 kilometers a second from LEO to the lunar surface, lands empty. Okay, but now it can be refueled on the moon. But what does that mean? That means in order to do the recurring mission, we have to lift the crew to orbit and we have to supply the LEV with 6 tons of propellant. A Dragon plus 6 tons of propellant can be done with a single launch of a Falcon 9. So now you have a recurring lunar mission, can be done with a single launch of a Falcon 9, $60 million per mission launch cost. Okay, this is in massive contrast to a program of record involving launching SLSs costing $1 billion each. Okay, and we are much more effective because we are based on the surface where we have propellant and we can do excursions anywhere on the lunar surface. The Deep Space Gateway is located in lunar orbit. Which orbit? Is it in polar orbit or equatorial orbit? Okay, if it has a polar orbit, it does have access to the poles, okay, but it's a large, that's the wrong orbit for staging Mars missions, okay? If it's an equatorial orbit, it has no access to the poles. And furthermore, it's not doing anything anyway. Okay, as the speaker from Marshall earlier, their lunar lander had its payload reduced by being forced to go to the lunar orbit toll booth. It didn't help their mission, it harmed their mission. So let's do an analysis of alternative mission modes for doing, well, let's compare this architecture, as it were, to alternatives. First, there's the program of record, which first construct a lunar orbit gateway, then use it as a node to send the Orion spacecraft to low lunar orbit and conduct a mission to the surface via lunar orbit rendezvous with a LEV-type vehicle. It only needs a delta V of 4 kilometers a second to go to the surface and back, but it has almost zero use as a flight system for exploring the moon otherwise. Okay, and then Orion returns the crew to aero entry at Earth. Option B is the same as the first, except we don't bother with the lunar orbit gateway because it doesn't actually add anything. Okay, option C is lunar orbit rendezvous, but use a Dragon instead of the Orion. Okay, this is the most obvious way to do the mission. This would be Apollo redone, except using a Dragon in the place of the command module, while using Orion, which weighs 3 times as much as a Dragon. Okay. And then once again a 4 kilometer a second left. Option D is a simpler architecture, and it's one that I supported until recently when I thought of this. Okay, which is deliver the Dragon all the way to the surface and fly it back directly to trans-Earth injection. Okay, this option has the advantage of simplicity. Okay, direct return. When lunar orbit rendezvous was attractive for Apollo because it saves mass, but it's actually a very unattractive option for supporting a lunar base, because if you're doing a lunar base, you don't want to waste manpower in lunar orbit not doing anything. If you're shipping people all the way to the lunar distance from the Earth, you want to get them to the moon where they can actually do stuff instead of keeping them, it's one thing to play Mike Collins while Buzz and Neil are kicking around dust for a few hours or a day or two on the lunar surface. It's nothing to be hanging up there for months saying, hey guys, I'm getting lonely up here. And then furthermore, lunar orbit rendezvous, you can only take off from the moon and rendezvous with a lunar orbit spacecraft at certain times. Direct return, the launch window to Earth is always open. That is, from a point of view on the surface of the moon, looking up at the Earth, it's always in the exact same point in the sky. You can, if you have to go back, you can go back any time. So direct return from the surface is very attractive from an operational point of view, but it's bad from a mass point of view until you have ISRU, and then it becomes okay. Okay, but then we have finally the moon direct thing, which is the architecture I just described. Let's look at the masses of these missions. Okay, we have phase 1, emplacement. Okay, for the first option that includes the lunar orbit gateway, I assumed it needed 120 tons mass in LEO to deliver that. which is, say, one SLS launch. That's probably conservative, but there it is. The others don't need that, so they all have just the mass delivered to the surface, which is the useful mass. Okay, then we have the phase 2, which is the manned mission. For these first two options, which involve sending an Orion all the way to low lunar orbit, as well as a LEV that is fueled, that does the excursion to the surface and back up to orbit, 126 tons each. You get a big savings by going to the Dragon because it weighs so much less than the Orion. Okay, so if you're going to do a conventional Apollo-style lunar orbit rendezvous mission, using a Dragon instead of the Orion is a big plus. The direct return mission, it's heavy because, and this is why LOR was adopted in Apollo, because you're delivering the capsule all the way to the surface and then having to shoot it back. But it is still doable within an SLS launch or 2 Falcon Heavy launches. Okay, and then the moon direct mission for this phase is about the same as the conventional LOR. But now look at the phase 3. The options A and B, 110 tons each, have to be lifted to orbit. Options C and D, 40 to 50 tons each. The moon direct mission, 14 tons. 1 Falcon 9. Okay. And then the total initial mass in Earth orbit, I assumed the full phase 1 for all options, 2 phase 2 missions, I assumed to be necessary to get things going, and then 20 phase 3 missions. You know, whatever, it's an ongoing program, pick a number. Okay, and what you see is the moon direct architecture, 500 tons to orbit, options C and D, 1,000 to 1,300 tons to orbit, and options A and B, 2,500 tons to orbit. Okay, so what we're going right now with is the worst of all possible plans. Okay, the obvious plan, option C, which is just do Apollo again but use a Dragon, okay, there is a significant improvement. But if we go with option E, we can cut the mass in half again and cut the recurring mission mass by a factor of 3 and have greatly increased surface access, an order of magnitude greater access to the lunar surface. Instead of 3%, 40%. All right. So, to conclude, the idea here is if you're going to the moon, take advantage of what's on the moon and design your architecture around that. Okay, this is how we've always been successful when we've explored. Successful pioneers have always taken maximum advantage of the resources that are available in the environment they intend to operate in. This is why Amundsen succeeded in the Northwest Passage and Franklin failed. Okay, this is, of course, why the Mars Direct mission is a significant advantage over missions that don't use ISRU. We have discovered ice on the moon. Let's use it. Thank you.